Welcome to Lecture Online, and here in this example we're going to show you how to find the moment of inertia of a solid sphere. So here we have a solid sphere of radius r, and it's going to be rotating about its center mass, and we're trying to determine the moment of inertia. So the best thing to do here would be to slice it up like this. So let's take a slice, like so. And of course that slice would have radius equal to x. So the radius would be equal to x, and if you think about it, that would be kind of like a slice like this. I guess make it look a little bit more like a slice. And so the thickness would be this thickness right here. That would be a dz, because this is the z-axis here. This is the x-axis. So the radius of that would be x, like that. And the volume of that, well, let's see here. The volume, the dV of that, because it's a small infinitesimal slice, would be equal to the surface area, which would be equal to pi x squared times dz. So that would be the volume of that slice. Notice, let's see here, if the mass of the whole sphere is equal to m would be the mass of the whole sphere, then let's say that rho is the density of the sphere, then the mass of that slice, so the dm of that slice, would be equal to the density times the volume of that slice. So, and you can see here, of course, that the density of the slice, or the density of that, would be equal to mass divided by the volume. And the mass, let's see here, I guess I used a small m for that, so the small m. So it would be m divided by 4/3 pi r cubed. So that would be the density of the sphere. The mass of the little slice would be the density times the volume. The volume would be equal to that. In other words, the mass would be equal to the density times pi times x squared times dz. All right. Now, the slice is like a disc that's rotating around. Of course, the moment of inertia of a rotating disc would be 1/2 times the mass times the radius squared. So that means that the di, and let me go over here. So the di, I call it a small little portion of the total moment of inertia, so we'll call it di, is equal to 1/2 times the mass of that disk, which is dm, times the radius of the disk squared, which would be x squared. So that would be the moment of inertia of that little disk. And of course dm can be expressed in terms of that. So that would be equal to 1/2, and dm would be rho times pi times x squared dz times x squared. So we can say that the di, if we just kind of rearrange the terms a little bit, would be 1/2 times the density times pi times x to the 4th times dz. Of course, if we now want to go ahead and find the total moment of inertia, we would integrate over all the little slices. And so that means that I would be equal to all the little di's, and that would be from minus r to r, because we're going to integrate across z from this position to that position. It would be from minus r to r, and that would be equal to 1/2 rho pi times the integral of x to the 4th dz from minus r to r. Now what I like to do is make things as simple as possible, so I'm going to integrate from 0 to r and simply double the integral. So 2 times this and integrate from 0 to r, so that means that I is going to be equal to twice that, which would be rho times pi times the integral from 0 to r of x to the 4th times dz. Now, of course, we still have a problem of making sure that we have the same variables there. We have an x to the 4th, we have a dz, that doesn't quite work, so we have to find a way to convert from x to z. So if I take this point right here, and I draw a line from there to there, and let's see here, if I take this angle here to be theta, and then I know that this is x, which is the same as this is x right here, and I can see that this is the vertical axis, so I can the vertical distance, and this is r right here. So I can say here that x squared plus z squared equals r squared. So let's do that. So we can say that x squared plus z squared is equal to r squared. So this would be z right there. And that means that x squared is equal to r squared minus z squared. So I can replace x squared by r squared minus z squared. And of course, since x to the 4th, I can say that x to the 4th is equal to the quantity r squared minus z squared, and if I multiply that out, I get r to the 4th minus 2r squared z squared plus z to the fourth. So I can replace x to the fourth by this quantity, and then I have my variables matched. So that's probably a good thing to do. So let's go over here and continue that integral here. So we have I, moment of inertia, is equal to the density times pi times the integral from 0 to r. And instead of x to the fourth, I'm going to plug in this quantity right here. So this is r to the fourth minus 2r squared z squared plus z to the fourth and times dz. And now that can be integrated. It's not a bad integral, so let's go ahead and do that. So we have the moment of inertia is equal to the density times pi times the quantity. That would be r to the fourth times z minus 2r squared times z cubed over 3, and that would be plus z to the fifth over 5, evaluated from 0 to r. Those are the limits. Now notice when we plug in the lower limit, we get nothing. When we plug in the upper limit, we get the following. So I is equal to density times pi times, so we plug in the upper limit, we get r to the fifth minus 2/3 r to the fifth plus 1/5 r to the fifth. All right, now we can combine what's inside the brackets, and then we can also replace rho for what rho is equal to right up here. Notice that this can be written as 3m divided by 4 pi r cubed. So let's go ahead and do that. So we have I is equal to, instead of rho, we're going to write 3m. We still have the pi in the numerator, divided by 4 pi r cubed times, notice the pi's cancel out, so I'll go ahead and get rid of that for now. Now here we have r minus 2/3 plus 1/5, so we need to find the common denominator. Common denominator would be 15, so it gives us 15 r to the fifth minus 3 goes into 15 5 times, that would be 10 r to the fifth, and that goes into 15 3 times plus 3 r to the fifth, the whole thing divided by 15. So we have 15 plus 3 minus 10, that would be 18 minus 10 would be 8/15 r cubed. So we have I is equal to 3m divided by 4 r cubed times 8/15 r to the fifth. And then of course this r cubed and r to the fifth becomes r squared. And the 4 and the 8 becomes 1 and 2, and the 3 and the 15 become 1 and 5. And now if I go ahead and finally add all that together, I get equals 2/5 times the mass times r squared, and that is indeed the moment of inertia of a solid sphere. So again, the trick is to go ahead and do the little slices. So here's a little slice. The distance from there to there is x. Notice x will go from 0 to r. And the thickness is dz. The volume of that would be the area times dz. And the mass would be the density times the volume, which can be written like that. So then we realize that if we then plug it in here, we get an equation with x to the fourth and a dz. X to the fourth can be written as r squared minus z squared quantity squared, because we know from Pythagorean theorem that x squared plus z squared equals r squared. And so we get, instead of x squared, we can take this. That is integratable when we put in the integral right there, and then the rest is just algebra at that point. And that's how we find the moment of inertia of a solid sphere.